Okay. Electrochemical, electroanalytical techniques. All right, so this is going to be other different types of electrical techniques in chemistry, collectively referred to as electroanalytical techniques, right? Literally analytical techniques that use electricity, okay? There are actually quite a few different types here, but notice they're all going to have sort of a common theme, which is you're going to use some form of redox reaction. You'll drive the redox reaction somehow with electricity or monitoring the electrical potentials, and then you'll get a measurement at the end, okay? There's several points that you can measure. You can measure how many electrons are consumed, right? How many electrons are used. You can measure another reaction coupled with it, or you can measure the final weight that comes off it, right? So electrolysis, this is the process in which a chemical reaction is forced to occur at an electrode by an imposed voltage. The most common electrolysis you see is the electrolysis of water, right? Which produces H2 and O2. Okay. And these are for like hydrogen fuel cells or whatever. Okay. Actually, this is not as common for hydrogen fuel cells anymore. There's better ways to do it. But people do this in their garage quite a bit, which is funny. Yeah. Like this is a very common and pretty fun, I've heard. I haven't ever done it in my garage, but I've done it in lab. So it is fun. So let's take an example. Suppose we dip copper and platinum electrodes into a solution with copper 2+, force the electrical current through to deposit copper metal at the cathode, and to liberate O2 at the anode. So here we have our two half reactions, cathode and anode. And there's our complete reaction with our total E naught for the cell. And we're comfortable with that so far, right? Okay. So what does this mean? Huh? Oh, yes, yes. These are reductions, yeah. Yeah. Oh, no problem. Yeah. Remember, this is the number for the reduction. This would be the oxidation, though. Okay. So it's they're trying to make this less confusing, but yeah.
So this is in the reduction form, right?
These are in the reduction and oxidation here.
Yeah, I forget what chapter it was, but it was always in like the oxidation form.
So the E naughts are always in reduction. So the ones listed in your book are always reductions. They just didn't bother flipping the sign here because, well, basically the equation in your book, if you go back, is the E of the cathode minus the E of the anode. And so they always list it in reductions here, even if they list this as an oxidation, which sometimes they don't. Sometimes they just list it as reduction, and they don't bother specifying here anymore.
Yeah. So I remember like all the other like half reactions and whatnot were always with the
Reduction.
Yeah.
Yep. Yeah. They flip this to the oxidation. They only do that in your book stuff when they're going to show the full reaction under it. Okay? Yeah. It's so you can assemble these.
So it's still like throughout, it would still have it the other way unless the
Typically. Yeah, your book's pretty consistent. I mean, it is written by humans. So, but yeah, your book's actually very consistent. So they typically do these half reactions as reductions, and then they don't specify the E naught here because E naughts are reductions. But because anytime they have the total reaction below and they're actually adding them together like this, they'll put this as an oxidation so you can add them together. And then they'll specify that this is a reduction, which is weird. I personally would have changed the sign.
Yeah, that's the part I was
Yeah. It's a little weird, But, you know, it's just a decision. It's fine. There's nothing wrong with that. You know you have to flip the sign. So, anyways, so you put these two together, this would give you your E naught cell, right? And so what is this E naught cell? Well, normally we've thought of these E naught cells as these literally being two different solutions that are separated by a salt bridge, right? And we thought of this would be the voltage that you would see going from one to the other if we were at unity, right? The standard conditions. But that wasn't the only thing that was, right? What if you put everything together in one? Well, then it would drive itself into equilibrium, wouldn't it? Okay? But there's another thing we could do. What if instead of having it just go on its own, we forced voltage across? So we hooked it up to an external power source and forced the voltage the other way. We provided the electricity, right? That makes sense? So what if we applied a voltage with an external power source of 0.893? Well, that means we could produce copper metal, couldn't we? Okay? And notice, for every 2 electrons we move over, how many coppers do we get? 1. So if we move over 100 electrons, 50 coppers, right? Okay, if we move over 2 moles, 1 mole of copper, right? Yeah. So, hey, is there some sort of number that you commonly get on electrical bills and everything else that tells you like a number of electrons, maybe over seconds? It's current. It's current, right? Yeah. So if you time a reaction, one of these, and provide electricity, time the reaction, how long you do it, and count the number of amps you do it on, like you do it 1 amp for a minute, you know exactly the number of electrons you put over. And this can be very well monitored. Do you know how digital equipment works? You guys ever heard of analog versus digital? Okay, so analog is where you look at changes in current and voltage, okay? And that's all it detects is, did the voltage change over a certain threshold, okay? And digital literally counts the electrons. That's how digital works. Now, it doesn't necessarily count individual electrons. Sometimes it counts packets, like groups of electrons. Not mole, usually more than, usually like much, much, much less than a mole. Yeah. A mole would be an example of a packet. More like usually like a 2 electrons, 4 electrons. Those would be the new systems. Most systems can't count a single electron. So that would be very difficult to set up. Okay, so the fundamentals of electrolysis. But it can, by the way, be set up. Yes, there are systems under which you can detect single electrons, and those aren't expensive necessarily. It's just how you set them up that matters, like the system which you set up. No, I'm talking more like use cases. Like you can think about it this way: if you counted everybody at the door, you can count them very easily, right? But if you just walk into a classroom and try to count everyone, that's much more difficult. More like how you have to count them and in what situations you can count them, that's where things get hard. Like you can count the electrons as it goes in like a CUDA core for a graphics card pretty easy. Okay, but there's other situations where it's much more difficult. Anyways, that's beside the point of this class. Okay? That would be like an advanced electrical engineering. That'd be a whole nother 4-year degree. All right. Again, this is your fundamentals of electrolysis. Notice in this case, Electrolysis, we typically look at a single solution. They are not separated from each other. There is no salt bridge, right? It's all in one. And that's because we're going to force the voltage across this, okay? So we are going to provide that voltage across this. Note here, this setup here is kind of interesting. This is a voltmeter potentiometer. This will tell you what your voltage is. And then up here we have an ammeter, which is an amp meter essentially. Okay, this is a terrible habit. I would prefer you guys not to learn it from me, but please know I will call these amp meters. It's not the right name. It's not a good way to do things. It's a terrible habit. It's gonna happen though, okay? So, sorry. Sorry. I hope you don't pick that up from me. It's a fucking terrible habit. This amp meter here, this is actually going to be connected here to your power supply, which would be your variable voltage source. Typically you want these to be variable so you can match the voltage to what you want it. Because you wouldn't want to have to make a new setup every time you do these things, right? One of these electrodes is going to be the platinum electrode. It's the one you do not plate stuff out on. The one that you do plate stuff out on will typically be a metal that you're trying to plate out on it, okay? So copper in this case. If that metal's not a good conductor, you may have to use something like platinum silver, but then that really increases the price and it makes it so you have to then digest the metal off of it later, usually with like an acid, and reset your electrode, your cathode, okay? So it's much better if you can just use like copper for copper, iron for iron, that sort of thing. It really sucks if you have to recondition your working electrode is what that's called, which is essentially strip shit off of it that you plated out. That takes a lot of work and time. Well, if you have the setup for it, it's actually not that bad, but the setting it up is just a nightmare. Okay, so notice the working electrode and you have a counter electrode. The working electrode is where the work happens. You plating something out on it, okay? The counter electrode is where the other half of that reaction occurs, right? So it would be your anode. And that can be anything, but platinum wire is usually best because a good conductor doesn't corrode, okay? Anybody have any questions about this? Notice that because you typically are plating out metals on these, most of these electrolysis setups are going to be the electrons go onto your working electrode. Okay? But you can do it the other way. Just, it typically is not useful. But that's actually how you can clean these electrodes if you're ever curious. It's one of the ways. And yes, have you ever heard of like chrome plated? This is one way you can do chrome plated. Have you ever seen those where they take like nickel or chrome plated and they, yep, that's this. Electrolysis. No, not typically, no. You can make mirrors like this. So I don't want to say that they don't because, I mean, you really could. But no, that's typically a redox reaction. So they spray a coating on the glass and then they form a redox reaction which puts the silver down. Okay. Back in the day, actually, the old ones, they used to beat the silver into a layer and then literally just put glass over it. So those are some pretty primitive mirrors. Those are the ones that make you look really weird. You ever seen those in like museums and stuff? Yeah, they kind of corroded on in between too usually because you know they're old. So knowing the current, that's I current, flowing through the cell over a period of time will allow us to calculate the charge that goes over, and the charge is directly related to the number of electrons, right? And that's what a coulomb is. So this is the equation, which would be the charge going over, total charge went over, equals the current times the time. Because remember, this would be your, is amperes, that's coulomb per second. And then coulomb is directly the number of electrons. But it's a unit of electrons, right? It's not a mole, by the way, but yeah, it's a unit. Okay, anybody, everybody okay? N is the number of electrons per molecule, by the way. So this would be 2 electrons have to go on copper 2+ to give you copper neutral. Faraday constant, of course, is coulombs per mole. This is how you can convert back and forth. This right here would be a summary of the moles of reactant, which is typically what you try to find in these things. So the moles of the reactant would be this formula. That's current times time over number of electrons. They're in the redox reaction. No, it's I. It's a cursive I. Yeah. I know. There's 3 different types of I. Anyways, time over number of electrons in that redox reaction times the Faraday's constant. This is an example of the problem. So if a current of 0.17 amps flows for 16 minutes through the cell that we saw before, how many grams of copper will be deposited? So the first thing we need to do is get the moles of electrons, right? By the way, if you use this formula, notice we've dropped this term from the formula when we're doing this problem, okay? If you use this formula, you get moles of reactants. We're doing it in 2 parts to better understand what we're doing, okay? So you take the current times the time. Notice the current is in per second, right? That means your 16 minutes have to be put in seconds, don't they? Okay? So times 60. You're then going to divide it by Faraday's constant. That's going to give you moles of electrons. So we have moles of electrons right here. Okay, we look then at the working electrode half reaction. That would be the cathode half reaction, right? The one that plates out the metal. So the copper has to have 2 electrons for each Cu deposited, right? That's why I made that big deal, like, remember? Okay. And so what does that mean? Well, our moles of electrons have to be divided by 2, doesn't it? And that will give us our moles of copper. So if you ever forget how this works or the equation here, you don't need that equation. That's literally a unit conversion, isn't it? That's all it was. If you know what an amp is, you can figure this equation out. It's that simple. An amp is a coulomb per second. So you times it by a time, divide it by a coulomb. There you go. See that? Strictly units. I never memorized this equation, ever, not once, in my entire undergraduate career. Okay, you all have a great day. We'll pick up here next time.